Hello. Today we are going to look at sets and probability. So how can we use what we understand about groups and sets to describe the probability of getting a particular outcome in a situation? So let's start off by looking at how we define probability more strictly in maths. So the probability is equal to the outcomes we want, the number of outcomes we want, divided by, so this is a dividing line, the total number of possible outcomes in a situation. Or put more briefly, the probability capital P is equal to the wanted outcomes divided by the total outcomes. If we take a particular outcome and we call it A, the probability of A would be written as capital P of A would be in brackets A. Now this is not multiplied, this means probability of A. So we're talking about probability, capital P, and we know we're talking about the outcome A because we put it in a bracket. And that's going to be the object of interest. And in set notation, that will be the number of elements in A, the number of ways that A can happen, divided by the total or the universal. Now, the probability of getting ahead when we flip a coin, we instinctively know is a half. But how can we use what we've just talked about to define it? Well, it would be P of capital H. So probability of getting ahead would be P of H, would be 1 out of 2, which is a half, which we already know, because there's one, when we flip a coin, we have one head out of 2 possible outcomes. We could either get a head or a tail. So there's 2 total possible outcomes. That's our universe. And there's one way of getting, there's one outcome of getting ahead. So we would say that we had a probability of 1 out of 2, what we wanted out of our total. So that's a brief notion on probability. Now let's put this into context with an example in sets. So we have a universal set of A, B, C, D, E, F, G, H. The set A is D, E, F, and G. Set B is B, C, D, E, G, and H. So let's draw a Venn diagram of this to see the situation more clearly. And as always, we start our Venn diagram from the inside, and we are going to work our way out. So by the inside, I mean we start at the center of our Venn diagram, the overlap of the sets, what is in both A and B, which we call the intersection. So we have the intersection of A and B. Well, D is in both. So I start with the first element in A and see if it appears in B, and E is in both, and F is not there, and G is there. So I have D, E, and G are all in the intersection. D, E, and G, and I know I put my dot next to each one of these to indicate that it is an element of the set. So D, E, and G are elements in A intersection B. Then we step outward and we take this bit here, which is going to be the parts of A that do not include B. So this would be A, not B, A not including B. And that's going to leave us with F by itself. It's the only element in A that isn't in B. And then for B, we would have B, C, and H are in B, but are not in A. So they aren't in the intersection. And then finally, we go out to our universal set and we see what hasn't been used up. So we can see D has been used up, E has been used up, F has been used up, G has been used up, B has been used up, C has been used up. They're already done, and H has been used up. So we are left with only A is outside of our sets A and B. So that's what goes on the outside. Now, for doing probability questions, this is a Venn diagram where we explicitly write out all of the elements. But in probability, we can see that we're majorly interested in the number of elements in a set, which would be the cardinal number. So we can draw another Venn diagram that only includes the cardinal numbers. And this is another style of Venn diagram that we can come across. So what would be the cardinal number of A? Well, A has 1, 2, 3, 4, or 1, 2, 3, 4. Again, if we're inside the circle A, we would include the elements. So there are 4 elements there. Cardinal number does not get curly brackets because it's literally the number 4. It's the number of elements. It's not a list of elements itself. Cardinal number of B would be 1, 2, 3, 4, 5, 6. Cardinal number of our universe is 1, 2, 3, 4, 5, 6, 7, 8. Count up all the elements in our universe. Cardinal number of A intersection B would be 1, 2, 3. Cardinal number of A union B complement. Complement means what's not or everything else other than what's in here. So everything other than A union B. Well, this is all of A union B, anything in A or B or both. And then we're just left with a single element, one element outside of that that's in our universe. And as we discussed up here, we have A not B. This slash here, the backslash here, means not. So A but not B would be the stuff that's in A but not including anything that's in B. So we exclude anything that's in B. What's left in A? Well, there's only one element there, the element F. And B not A would be all of the stuff that is in B, but nothing that is in A. So that would leave us with 1, 2, 3 elements. So now can we use that to fill in our Venn diagram? Well, as always, we start in the center. So we have A intersection B would have 3 elements. We can read this directly from our original Venn diagram as well. We have 3 elements in A intersection B. We have 1 element only in A, or in A not B. We have 3 elements in B not A, and we have 1 element in A union B complement. So what's outside of A union B? And we can fill in square brackets the totals. So the total in A is 1 and 3 is 4. That's the total in A. So these are the cardinal numbers I'm writing in here. And the cardinal number of B is 3 and 3 is 6, which is the same as what we had up here. So now we've filled in this cardinal number version of the Venn diagram. It may help us with doing our problems here, because if we want to know the probability of A, so if we imagine that these were a bunch of pieces of paper that we wrote all of these letters on, all of the letters are on our pieces of paper, and some of them are in group A and some of them would count as being in group B. The probability of getting one from group A would be the number of letters we have that's in group A divided by the total number of letters that we created. So that is going to be the cardinal number of A all over the cardinal number of our universe. The wanted outcomes, so we want something from the group A, so we have 4 letters in the group A out of a total of 8, and we can simplify that to being a half. So we have a probability of a half of if we had all of our letters on the table and we picked one up at random, we would have a probability of a half of getting a letter that was from group A. And from group B, we have the cardinal number of elements in group B divided by the cardinal number of our universe, because that's the total we are working from, which would be 6 out of 8, which would simplify to 3 out of 4. Now, the probability of A intersection B would be the number of elements in A intersection B divided by the number of elements in the universe. So that's 3 elements in A intersection B divided by our total of our universe. There are 8 elements. A union B. Probability of A union B would be cardinal number of A union B all over cardinal number of the universe. Would be, we have 1, 2, 3, 4, 5, 6, 7 elements in A union B, and we have 8 elements in the universe. So we have very good odds of getting a number, or a letter I should say, from the group A union B. Now I'm not going to stop writing this for the last two because they'll get a little bit messy to try and write neatly in here, but you can always write down what it is you're doing. So we have probability of A union B complement. Well, that means, well, actually, let's just write it down. We have cardinal number of A union B complement all over number of elements in our universe. Well, we know there's only one element outside of A union B, so we want all of the elements that are not in A union B. Well, there's only one of them, so that's going to be 1/8, and we can see the probability of getting a letter from A union B plus the probability of getting a letter that is not in A union B would add up to 1. It would add up to 8 out of 8, which would be 1, which makes sense because we'd certainly get a letter that was either in A union B or not in A union B. And that will be an important idea in probability in the long run. And then finally, we have probability of A intersection B complement. So probability of getting a letter that is not in A intersection B. Is going to be 1, 2, 3, 4, 5 out of 8. And then finally, a little bit of recap. Is A, our little symbol here means element, is A an element of A union B? No, it is not. To be an element of a set means it should be inside of our circles, or for the union, it would be inside A or B or both. But we can see that it is not in there, or it would appear in our lists for A or B, and it does not, so we would say that that is false. A is not an element. The element A is not an element of the sets A and B. And is F, D a subset? So our long C means a subset of B. Well, D is an element, but F is not. So this wouldn't be a subset because all of the elements in this set are not contained in B. So we wouldn't say that it was a subset because one of the elements in this set is not in B, so it is not a subset, a subgroup of B. And that is what we need for an introduction to sets and probability.